want to see calculations on it. Then we look at boiling. And boiling and evaporation, if time permits us. Now, last week we were able to look at specific latent heat of vaporization of steam, and we define it as quantity of heat required by a unit mass of water to change heat from water to vapor at boiling pump without changing temperature. And you are told that the quantity of heat required, in other words, the quantity of heat lost by the steam to condense to water, can be calculated by using, this is just a reminder, by using Q equals mass of water specific latent heat of steam. We can say steam. That's it. So the boiling water is where you can say where Q stands for quantity of heat lost by the steam. Then of course M stands for mass of water. Then L steam, as you have said, steam equals specific heat, latent heat of vaporization of steam, or simply say of steam. So we can calculate the quantity. And I remember before we closed last class, you are given when the steam condenses to water at 100 and water cools down to lower temperature, we can determine the heat lost by the steam. So we want to have some calculations today, and we see some other mixture. But before I give some calculation questions, may I ask you if you have any question for me, or maybe when you are practicing question on this topic, you have some question that pose problem to you. Can we have such questions from you before we proceed? We have done specific capacity, we have done specific latent heat, or fusion, or vaporization. Questions under heat generally, if any. Let's have it. Today's class is tutorial class. Then, yes, any question from you? No question? That means you did not practice anything. That's the implication. Or you want to tell me that every question you practice at home, you get them. Can you prove that you work some questions on your own at home? Who want to show us, prove to us? You show me the evidence, give all the questions, and tell us how you go about it. If you did not work questions on this topic at home, raise up your hand. Let me see you. Now, you give me a reason why you refuse to work. Is it that you don't understand or don't have material to lay hands upon, or what? Why didn't you solve some questions? Yes, yes. You don't understand? Louder. You do or you do not? You do not understand the question. Have you attended the class throughout? Did you attend any question that you could not solve? Yes, how about you?
Nothing.
What is nothing? You don't understand the topic. Because when you have not learned, then it means we've not taught. We have to repeat the topic. We you work any question you cannot solve? Can I have that question? Hello, do you lay hands on any question at home? Then I don't believe you. Yes? Did you attempt any question at home? Why? How about you? Why? Since when? We started this almost 2 weeks ago. So you have not had timetable on your timetable since 2 weeks ago. That's funny. Yes, next. What is the meaning of head you are checking? Let me have some of the questions you solve you don't get. Bring it out, we'll see it together. Yes, next. Wait, what is it you don't understand?
And the last one.
Before the last one, did you attempt any question on your own? What do you say?
Yes, sir.
Let me have those questions. Yes. You did not come. Come when? Okay, before Wednesday and Thursday. Did you lay hands on any question before?
Yes, sir.
And you get them?
No.
Where are those questions you did not get?
Exactly.
So you will know from those questions you did not get, you will know it at home.
I forgot to check that.
Then, after you have attempted the question, have you not come to this lesson after that?
I don't have any of that on Friday.
Oh my God. You sit down. Sit down. Well, we thank God that majority of you said they have worked questions on that. Only very few. We will not go back because of a few of you, because that won't permit us to do that. I believe by the time we finish the calculation we have today, you will pick. But if you don't pick, then I have to start with you, maybe online. Do you understand? Those of you that do not understand this, I will have to give you a number. I will give you time outside this to repeat the topic with you. That is going to be online, if that is what you want. And everything done are recorded. By the time you go through all that, you still don't understand, contact me. Then I will know what to do. Is that clear? Please let me have your name. Those of you that stood up earlier, let me have your name. And you will do yourself a favor. As from today, pick a question that the topic. Attempt it to the level you can go. Forward the question to me and your solution, so that I'll be able to pick you up from wherever you are, if you actually want to learn. Do you understand?
Yes, sir.
Don't just sit down and say I don't understand. No. If I ask you what is heat capacity, can you define heat capacity? Define specific latent heat of. Define it quickly.
Can be defined as the heat required to change a solid to liquid without changing the temperature at melting point.
You don't need to cram anything. When you understand it, you say it. You can say it in your own English. Just make sure the idea you are making across is correct. We define that, sit down, quantity of heat required by a unit mass. Everybody should be able to define this. A unit mass of a solid substance to change it from solid to liquid at the melting point without changing temperature. You should sing it. Not say, but you should sing. What you know very well is what you sing. And you don't need to cram it. So simple. We define specific capacity, we define specific density of fusion, and I said, that time when I was taking it, I said, it's like when you say students, that's a general statement. But when you mention name, a particular person bearing that name, we answer. It's quite different from saying student generally. But if you say Shola, any person that bearing that Shola will answer. But if I say student, nobody will want to answer that because student belongs to everybody. That's when you define heat capacity. It's just a general definition. Quantity required by a substance to change its temperature by 1 degree Celsius. A substance. But when you say specific, that's when you had a unit mass. This is very simple. When we are defining specific latent heat of fusion, we said is the quantity of heat required by a unit mass of substance. If it is fusion, by unit mass of a solid substance, to change it from solid to liquid at melting point without change in temperature. That should not pose problem to anybody. And last class, we look at that of steam, vaporization. And I said remove solid and put liquid now. How do we define vaporization? So the latent heat of vaporization. Quantity of heat required is defined as quantity of heat required by a unit mass of liquid substance to change from liquid to vapor at boiling point without changing temperature. That's so simple. But steam, specific latent heat of steam, that means water changed to steam. Instead of saying a unit mass of a liquid now, it will now be a unit mass of water to change it from water to steam at boiling point without changing temperature. It is what you want to know, you will know. If you don't want to know, you may not know. And if you want to know, it is bit by bit you learn. Now, as I said, we want to look at some calculations. When dry ice block, listen to this. We have some dry ice block. The ice block is solid. Let's say the ice block is at 0 degrees Celsius. And you have warm water. Keep in a calorimeter. We have calorimeter that is large. To large is to prevent heat loss by conduction. You put insulator around the calorimeter. Then you pour some warm water into this. What do you need to know? You will need to know the temperature of the water in the calorimeter. Give me a temperature. That certain temperature of the water in the calorimeter. Just mention anything. What do you say?
80.
Now, if you say the water here is 80 degrees Celsius, then the ice block, this should be dry ice block. Piece by piece you drop and start. Piece by piece you drop and start. So, if you drop this quantity of ice block piece by piece into this and you start, when the ice block is dropped here, I want to ask a question. Piece by piece you drop ice block into this. What do you think will happen when ice block is dropped or are dropped into the water kept in the calorimeter here? The water in the calorimeter is at 80. Ice block is at 0. What and what we lose or what and what we gain in? Ice block is dropped into this. What and what we lose, what and what we gain. Yes?
Water and a container will use ice block. Why ice block?
Please clap for her. And you say you don't understand. You are lazy. Some of you are lazy. I've given you what can make you understand the calculation, but you never read, go over it. She gets it correctly. Please sit down. Ice block, I told you, we always gain heat. From where? From its environment. But now, the ice block is now dropped into this water at 80. So, you don't need anybody to tell you that the ice block will be gaining heat from the water and the calorimeter. That is very correct physics. So, if you want to now state the mathematical expression for that, what will you say? Heat loss by water and calorimeter will be equals to heat gain by you gotten the problem solved. Another hypothetical thing you need to know. I want to know who is going to tell us that. Supposing the mixture temperature is 40 degrees Celsius. That's steady temperature. What happened to the heat gain by the ice block? What happened to the heat gain by the ice block if the mixture temperature is 40 degrees Celsius? Can somebody tell me that? What happened to the ice block if the mixture temperature is 40 degrees Celsius? We already know that ice block gain heat. So what will the ice block do with the heat gain by it? Yes? You want to try? I will talk to you if you try and you get it. That means you are deceiving me. Yes, let's hear from you.
It will melt. The ice block will melt.
Yes, it will melt. That's all you know? Okay. Baptist boy, the boy at the back, I'll force some of you to talk. Don't waste our time. Talk.
The ice block will gain it until its temperature reaches 40 degrees Celsius.
Put it properly. It's not properly stated.
The ice block will gain it and it will increase the temperature.
Okay, the ice block will gain heat and the temperature will rise until it becomes 40.
And it will maintain the thermal equilibrium.
The ice block will gain heat and its temperature will rise until it becomes 40 and maintain thermal. Yes. The guy in the job, what do you think will happen? Fast, don't waste our time. You can sit down and talk. Just raise up your voice.
The ice block will melt and it will turn to 40. The temperature of the water.
You didn't state it very well.
The ice block will melt and the temperature will be 40 degrees Celsius.
How? Okay, what I expect you to say, sit down. What I expect you to say is the heat gain by ice block will be divided into two. Part of the heat gain will convert it from solid to liquid. That's somebody understanding. The remaining part of the heat gain will raise temperature from, that means part will convert it from solid at 0 to water at 0 inside that container. Then the other part will now raise it from water at 0 to water at 40 in the same container. Do you understand what I mean by that? Everything, yes sir. And after that you say you don't understand. Now what happened is this. Calorimeter and its container. Okay, water. Water is H2O. Then calorimeter is this. Now the block, solid block. This is the block at 0 gains heat. This is ice at 0 degrees Celsius. We come to gain heat to become, you must understand it before you can solve question correctly. So the ice at 0, we need heat to change it to water at 0. This is now water at 0 degrees Celsius. That's Q equals mass of ice. The heat gain by ice will first of all convert it to water at 0. Then water at 0 will now be raised to water at 40. This will now be water at 40 degrees. The part of the heat, Q1, this is Q2 now. Q2 will be mass of ice, density of water, changing temperature from 0 to 40. That's what you are going to have now. But this one is at 80. The water and the calorimeter have initial temperature of 80 degrees Celsius. 80 degrees Celsius. Cool down to water at 40, whereby they all have the same level. The water at 40, everything have the same. This is 40 degree, 40 degree, then 40 degree. This one cool from 80 down to this. The water at 80 cool down to 40. Calorimeter at 80 cool down to 40. Ice block change from ice block solid to water at 0. Water at 0 is raised to water at 40. So it means this is lost and this is gain. Q1 and Q2 are gain. Do you understand that?
Yes, sir.
A boy in class like myself, do you understand that? What happened in that container is ice block will not remain as solid. It will change to water in that container from ice at 0 to water at 0. Then water at 0 will be raised to water at mixture temperature. You must have this knowledge before you can solve question correctly. If you don't have that knowledge, you may not be able to solve the question correctly. Is that clear to you? So mathematically, I can express this. How? I can simply say heat lost by water. That's the mathematical expression before I give what I want to give. You can simply say heat lost by water and cargo equals heat gained by height. So you have physics there will now be heat lost by water. Heat lost by water and cargo equals heat gained by ice block, of course. Ice block. You have ice block. Once you mention that, that is physics, and that carry the larger part of the math. So you can translate it to mathematics. How do I calculate it lost by water? That will give me mass of water, so capacity of water, change in temperature of water, plus mass of calorimeter, the capacity of calorimeter, change in temperature of the calorimeter. That will be equals to heat gained by ice, because the ice is at 0 degrees Celsius. We only do things to convert it to water at 0 and to raise temperature of water at 0 to water at mixture temperature. Cleared? Don't just busy writing. Listen to that explanation. So that is what we use to solve questions. So that is going to be heat gained by ice block will now be the part. I've shown the diagram to illustrate that. That will be heat gained by ice will be the one that converts it from solid to liquid, plus the one that raises it from water at 0 to water at mixture temperature will still be ice that turn to water, stress capacity of water, change in temperature. The change in temperature here now. Now, this is mathematical expression of what is stated above. This is mathematical expression of what is stated above. Every other thing is purely mathematics. How? You already know that this one comes from 80 to 40 in this diagram above. So I will just put it as M of water, so the capacity of the change in temperature will now be from 80 to 40 in that diagram. Then plus mass of calorimeter, the capacity of calorimeter, change in temperature will still be 80 minus 40. That's change in temperature in the two body that loses heat to ice. So, and of course, we know mass of ice, latent heat of ice, change in temperature here, the second water inside the calorimeter will now be, you raise it from 0 to mixture temperature, because mixture temperature is 40, this will be minus 0. So whatever thing the question wants you to calculate will now, other parameter will be supplied, only one will be unknown, and that is the one the examiner will ask you to calculate. When you are talking of mixture, mixing two things together. Here now, we are talking of mixture of ice block and warm water. And warm water does not just exist by itself, it has to be put in a container. and that container too, unless the examiner tell you that the container has negligible thermal capacity. Once you are told that it has negligible, that simply means the heat gain or loss by the container is very, very small. So you can ignore it. That's if the question say it has the negligible heat capacity. That means you can recognize its loss or gain by the container. So when you are told in the question like that, you may not consider the container. But if the question, the examiner did not tell you that the container has negligible thermal capacity, you have to consider it. Or if the examiner is silent about the container, you don't need to use it. So I have some questions for you. So let me give the question out and see. So this one will be example 1. I have explained what we need to do. So looking at this, I will write and also read as I write. So if you don't see what is written, you can listen to my voice and put it down. So still under mixture. So example 1, 150 gram. 150 gram. Gram of ice at 0 degrees Celsius. 150 at 0 degrees Celsius is mixed with 300 grams of water. 300 grams of water at 50 degrees Celsius. Calculate the temperature. You have to calculate the temperature of the mixture. You have to calculate the temperature of the mixture. Then you have to take specific latent heat of fusion of ice to be 3.34 times 10 raised power 5 joules per kilogram. Then you are also taking specific heat capacity of water to be 4,200 joules at Kelvin. This is one of the simple thing question. If I may ask, who want to solve this question for us? This is a simpler question to the explanation I've just given. Now, okay, have you finished writing? You are still writing. Who want to attempt it? Are we still writing question, or why are we our hands down like this? Are we solving it already?
Yes.
No. Just let's do it together. Have you finished writing the question? Close your book, drop your pen and close your book, and look straight to the board. I don't want a situation that somebody will say it's not clear, I couldn't solve anything. Let's discuss it together. This is simpler than the illustration I explained earlier. How many things are we talking about in this question? Who want to tell us? How many? Your hands up. Just interpret the question. How many substances are we talking about here? Yes?
3.
3, yes?
The eyes.
If you cannot stand, you can sit down and talk loud. Yes.
The eyes.
The eyes block.
The ice block.
Yes.
The water and the container.
Did they mention container there?
Nobody.
But what?
It will be inside the container.
It will be inside the container. But I said it earlier. Please clap for her. Please, I want everybody to be in the class. The aim and objective is for you to understand it in the class. What you are jotting down, you can take any test, you can go to the net. When you understand, you will be able to read anything and get it. So now, do not supply yourself what the question did not mention, or what is not part of the question. Do not. I said it earlier that if they do not talk about container, you ignore it. How many of you had me saying that before? The container is not mentioned here. We know for sure that water cannot be alone. It has to be in the container, but no parameters, nothing about container is supplied. So you don't bother yourself with that. So as it is, this is simpler. We are having just 2 things here. What are the 2? You have ice block and water. The 2 of them are these, just the 2. Ice was at 0. Water was at 50. Mass of water was given. Mass of ice was given. Mass of water was given. What did they need? The mixture temperature. Am I communicating? Before you can solve this question, you ask yourself, ice is at 0. Water is at 50. What is losing? What is gaining out of the 2? Which one is losing? Which one is gaining? I don't want cross answer. I don't want to contribute. You raise up your hand. The guy at the middle without cap. Yes. Which one is losing? Which one is gaining? Okay, clap for her. Yes. If you know water is losing, the heat gained by ice will be divided into what? 2. Can you tell us? Louder, louder, louder.
For the ice.
What do you mean by for the ice and for the water? Okay, who can say it better? Yes.
For the ice to convert into water from 0 degrees Celsius of ice block to water, and from the water at 0 degrees Celsius to water at 50 degrees Celsius.
Can you hear him at the back? Well, because of time, what I have said earlier here in the diagram, yes, we know there are 2 things. She has just told us that water was at 50. Ice block. The ice block is solid. And we are told that the ice block is 0 degrees Celsius. And for this 0 degrees Celsius, any heat gained by ice will change the ice to water at 0. So heat gained by ice, we do one thing. And what is that? Convert this one to water at 0. That's the first thing, the first part of the heat gain. Or the heat gained by ice, we first of all do the work of converting it to water at 0. This is water at 0 now from ice at 0 degree. Ice at 0 degree, you have ice at 0 degrees Celsius. Change to water at 0 degree. Then water at 0 degree now will now be raised to a mixture temperature which we do not know. This is now data M, we do not know. This comes from 50 degrees Celsius and it comes down to a temperature we do not know, and that is mixture temperature. the examiner wants you to calculate this, and the question is, what is this? Do you understand that? Yes. Some people do not respond though. Do you understand it? Those of you that stood up earlier, do you understand? Yes. Good. I will catch you another class. Now, solution. Let's quickly solve this. In the first instance, what we need to say is heat will be lost. Heat lost by water. Heat lost by water should be equal to heat gain by ice loss. Then how do we now translate it to mathematical expression? Heat loss by water will be mass of water, specific capacity of water, changing temperature. Good of you. Then this will now be, we already said it, that the heat gain by height will do two things. Two jobs will be performed by the heat gain by height. One, to convert it to water. How do we calculate that? Mass of ice, latent heat of ice. Then we add it up to the remaining part of heat gain by height, which raises the temperature of water at 0 to water at mixture temperature. That's delta theta. So simple. Once you have gotten to this level, every other thing is mathematics. Where you can go further. So it means mass of water, you are giving mass of water.
Yes, sir.
Of course, you can list those one out. What is the mass of ice? Initially, you can say under solution, mass of ice, Mi, is 150 grams. I told you last class, depending on what you are supplying, all these are kilogram. That means masses in gram needs to be converted to kilogram. 1 is kilogram. You divide by 1,000. Similarly, you have mass of water too. Mass of water, MW, which is 300 grams, will be converted to 0.300 kilogram. And the initial temperature of ice is 0. Initial temperature of water is 50. Now I transfer that to this. I can say mass of water, the capacity of heat. Change the temperature now can be the final temperature minus the initial now of water is 50. Subtract the mixture temperature from it. That means this. I'll show the diagram there. Then, which is equal to mass of ice, latent heat of ice, plus this time around mass of ice, so the capacity of water. Change the temperature here will be mixture temperature minus 0. Because you raise the temperature from 0 degree to mixture temperature. That's why we have it like that. Once you have written this, what else? You substitute for what you are given. We are giving mass of water to be 0.300 times 4,200 into 50 minus theta m, and equals to mass of ice is 0.150 times the capacity of this, which is 3.34 times 10 raised to 5. That's it. Then plus 0.150 times 4,200 into theta minus 0 will now be theta straight away, theta m. That's it. So you simplify this with your calculator. To those of you who want to write down, you can change this one to fraction. Even without calculator, you change this one to fraction, you simplify. This is, you can say 3 over 1,000 times this. It reduces that. So it will now be, remove this 2 0 here, and you remove this. That will be 0.3. if you do that. So multiply this by 3. With your calculator, you can turn it to be 3 times 40 times 50. Then minus 0.3 times 4 to theta times theta m. Then equals 0.150 times 3, 3, 4, 1, 2, 3. Yes, that's it. Then plus 0.15. You can turn this one to the same way you did the other one. This can be 150 all over 1000 times that. And if you cancel 2 zeros, what do you have left? Yes, what is it? Yes?
The mass of water.
Yes.
It's supposed to be 0.003.
Mass of water is 300 divided by 1000. You can change it to fraction and multiply like that. That's if you don't want to use calculator. But if you want to use calculator, you multiply straight away. Now this 300 all over 1000. Change it to 300 all over this. We cancel this 2. Then you have 3 over this. Then you now listen. Now the most important thing after this, you can use calculator. But if you don't want to use calculator, you can use fraction to do it. How do we use fraction is what I'm making across. Now to use fraction, what you do is, if you convert this one to 0.3 multiply by this, then you can turn it to become 3 over 10. That's if you don't want to use calculator. But if you have your calculator, you multiply straight what you want to do, and that will become simpler. It's not a big deal to do that. Now, this is 4,200. Then you have 0.3 times 4,200. The best, if you quickly calculate, is to use calculator. To do that, it will reduce all the jargons you have here, and it will choke your calculation. But I'm trying to simplify by saying, okay, if you don't want to use calculator, how do we solve it faster? This one too. This one will now give us mass of this is 150 all over 1000. Then this cancels this. Then if it cancels, you have 0.15. And this will give you 0.15. Even if you put 0 here, it still made the same. Then what is given in standard form can be reduced to ordinary number times 334,000 from standard form to ordinary number. Then plus 0.15 times 4200. 0 minus this will give you theta A. Simple. Now, you should understand that it is not the final answer that matters. But what I want to make across to you is, how do I use solve expression without using calculator? I can as well say, okay, go home, take your calculator and get the answer too. Am I communicating? Yes. So, what happened to that girl? So, if you have a question like this and you don't want to use calculator, what do you have to do? Turn this one from decimal to fraction, and it will reduce the whole thing. So I want to turn it to fraction. 3 over 10, we cancel this. And what do you have? You have 3 times 420 times 50. That's it. Then minus 3 times 420 times theta. It reduces it into this, which is equal to this one too. You have 15 times 3, 3, 4, 0. 2 will have gone. Then plus this will be, who are those people? 15 times, remove 2 here, 42 theta. So everything becomes simple. How? What you have here can be 3 times this straight away. And even this one, 3 times 2, that's 6, 0. That's 3 times 4, 120. I mean, 3 times 4 is 12. This is this. Then you multiply by 50. 1 0 will join this. That's 5. 5 times 6. 5 times 6 is 30. Then you write 0 here. Remainder 3. 5 times 2. 10 plus 3. 13. Then 5 times 1. Then plus 1. Are you with me?
Yes, sir.
So that will be what? Plus 1. 6. Then minus 3 times 0. 0. 3 times 2. 6. 1, 2. Very simple. It's not only depending on calculator until you see calculator before you can work. That's what I want to make across to you. You can turn it to standard form. You can turn decimal to a fraction, yes, and simplify. 2 or 5 or 3 can go, so that the whole expression will become simpler. You need to know all this method and use the method when you are solving. Depend less on calculator. That's what I'm making across. The answer to this question is not what is important to me, but what you are gaining. How do I solve complex questions without calculator? Am I communicating?
Yes.
Any questions on that? Okay. So, yes. Now multiply this by, how do I do this? 15 times 0 will give me 0. 15 times 4, that's 60. You write 0. 60 remainder 6. 15 times 3, 45. You add 6 to 45. What do you have? 51. So you write 1. Then 15 times 3 again. Plus what? Plus 5. 50. So plus, now 15 times 2 here, 30. Remainder 3. 15 times 4 plus 3. That's it. Then you collect the like terms. Our like terms here will give us 6300. 6300 minus 50100 equals 126 0 theta m plus 630 theta m. Is that clear to everybody?
Yes, sir.
So what you actually need will now come out. When you add this together, 0 plus 0 will be 0, then 3 plus 6 will be 9. So you are having, don't want to rub that. So if you add that together, you can take it off from subtraction first. So 63,000 minus 50,100.
12,000.
Good of you. 12,900 equals 1,890 theta m. Therefore, theta m will become 1290 all over 1890. So what do you have?
6.83.
6.83 degrees Celsius. That's the air. You can have it now. Quickly. You can quickly have that. quickly have it down. I have other 2 questions, but time will not permit us. I will give them to you. You go and do them at home. So maybe next class, we use the first 5 to 10 minutes to give the correction in the class. So I want to see how far you can go about it. Quickly jot what you have down, then I will dictate the last 2 questions. And I want everybody to go and practice 5 different questions on heat capacity, specific capacity. You bring it to the class next class. Evidence that you do what you are asked to do must be brought to the class next class. So take the textbook you have under heat capacity and specific heat capacity. Then you also look at exercise under specific latent heat of fusion. Solve 5 different questions and bring the question to the class. I have some questions I will give to you here. So if you fail to do that, next class you are going to be given classwork. And if you fail to attempt, you are going to be dealt with. Are we good to go? Some people are still writing. Now, take it down because of time. Dry steam, dry steam, dry steam, dry steam at 100 degrees Celsius. I said dry steam at 100 degrees Celsius is bubbled into 500 grams. Bubbled into 500 grams of water. What will be originally at 20 degrees Celsius? I take it again. Dry steam at 100 degrees Celsius is bubbled into 500 grams of water, originally at 20 degrees Celsius. What will be the temperature? What will be the temperature of the water? After 30 grams of steam has condensed, specifically take specific latent heat. Take specific latent heat of steam to be 2.26 times 10 raised power 6 joule per kilogram. 2.26 times 10 raised power 6 joule per kilogram. comma, specific heat capacity of water. Specific heat capacity of water. 4,200 joule per kilogram per Kelvin. Number two, calculate the specific capacity. Calculate the specific capacity of the materials for which the heat supply, comma, mass and temperature rise are given below. I'll take it again. Calculate the specific capacity of the materials for which heat supplied, mass, and temperature rise are given below. 1. 2.52 times 10 raised to power 4 joules. 2.52 times 10 raised to power 4 joules, comma, 0.3 kilogram. 0.3 kilogram. And 20 Kelvin. That's Roman figure 1. 2. Roman figure 2. 8 times 10 raised to power 3 joules. 8 times 10 raised to power 3 joules. 500 grams. And temperature from 20 degrees Celsius to 60 degrees Celsius. From 20 degrees Celsius to 60 degrees Celsius. Roman figure 3. 9.45 times 10 raised to power 3 joules. 9.45 times 10 raised to power 3 joules, comma, 150 grams. And from 15 degrees Celsius to 45 degrees Celsius. Solve this against next class. All these questions are taken from New School Physics. In case you miss any, search for them in New School Physics. There's another one I've written out. Next class, we are going to do that one as class work here. So, any question for me? I hope Wednesday nobody will come to the class and claim that I do not understand.